So let's we will start in a few minutes. Let's see who joins, and we will start in a few minutes. So let us start. So I hope I am audible. So the name of this course is Defects in Crystalline Solids Part 2. Means this is an advanced part of Metallurgical and Materials Engineering. This course is being taught in NPTEL by Professor Shashank Shekhar. So I am an PMRF TA for this course. So I will be taking some live sessions, particularly one live session each week. So this is a 4-week course. So there will be 4 live sessions every Saturday from 4 p.m. Today is the first session. So let's get started. The course outline. So in the first week, is about FCC, or the face-centered cubic structure. So we will learn about dislocations in the FCC. So there it is divided into subtopics. So if you look at the NPTEL, there are I think 5 videos, there are 5 lectures there. So the professor talks about partial dislocations, Thomson's tetrahedron, dislocation logs, stacking faults, twin boundaries. Okay. So we will look at them. We will learn some of the concepts, the fundamental basic concepts associated with these terms, and we will see. So just let me ensure once that the video is recording. Okay. So let me start. So what is dislocation? So in material science, a dislocation. So dislocation is a linear crystallographic defect or irregularity within a crystal structure, which leads to a change in the lattice, which leads to an abrupt change in the arrangement of the atoms. So what happens is the structure around the dislocation changes. Okay, although at some point far beyond the dislocation the structure is retained, but around, it means in the neighborhood, there is a change. Now these dislocations can slip, so we know that. So let us learn that in details. So the movement of dislocations allows the atoms to slide over each other at low stress levels, which is known as the glide or a slip. Now we will, as we will learn later, so the dislocations can be extended or partial. And basic in the, this is the part 2 of the course. So in part 1 we have learned the main deformations are the point defects and the line defects, and the line defects are the dislocations. Now in dislocations can be partial or extended, And plastic deformation of a material occurs by the creation and movement of the dislocations. And a very important factor is that the number and arrangement of dislocations influences the material properties. So this is very important in metallurgy. So in the metals and the alloys, they exhibit different properties depending upon the movement and the arrangement of the dislocations. So we will first look at the basic, what is dislocation. So dislocation is a linear crystallographic defect, we have learned it. So this is an basic structure, a schematic or a cartoon of a dislocation. So you see this is a crystal lattice. So we are for simplification we are looking at a two-dimensional crystal lattice, right? So this is pointer here. So this is my x-axis, this is my y-axis. So this is a two-dimensional lattice, and these are the lattice points which are occupied by the metal atoms. And here, so this is a ball and stick model. So this is not the hard space filling model. So it is ball and stick model. That's why atoms sizes are small. So for clarification, better understanding. So you see, so what happens is this. So this is not a line. Okay. So this is a plane of atoms. So if this is one plane of atoms, this is a plane containing atoms, and if we look at from the front we can see the plane, but if we look at from the side like this, then we will see a thin line. So here also these lines actually represent a planes of atoms. So this is a plane, this is another plane, third plane. Now when we look at the fourth plane, so the fourth plane vanishes in the middle, right? So this here is what is created is a dislocation, right? So this is called as what? This is called as the extra half plane, and the area below that is called as the missing plane, right? So you see, here we will understand it in a better way. So this, as I explained, so these are not lines but planes of atoms, and the planes, the place where the extra half plane ends, below that we can call as a missing plane, and this missing plane where this extra half plane ends, we call that as a dislocation. Okay, so this extra row of atoms, so this is the extra half plane, it has been marked, and the area below that is the missing plane, right? So how is this denoted? This thing, if I try to draw, so it will be somewhat like this. So this here is the extra half plane, and on both sides it will be like this, right? So this area is the missing plane. So this area, how it is denoted, so it is denoted like this. This is the dislocation. Okay. So this is the schematic, the basic schematic. Now in the first part of this course, so we will learn about dislocations in FCC. So what is FCC? FCC is the face-centered cubic system, right? So one basic thing is that in crystallography, we have the cubic systems, right? And in the cubic systems, we have this face-centered cube. So this is face-centered cubic system is a very small part of the entire crystallographic, right? Right. So there, as we know, we have learned, so there are 7 crystal systems, right? So when we start, if we go symmetrically, then the crystal system with the lowest symmetry, so that is called as the triclinic, right? So we have the triclinic, then little much more symmetric, we have the monoclinic, then we have the orthorhombic, higher than that is tetragonal, we have trigonal, hexagonal, and then at number 7 we have the cubic. So in cubic, so what happens, so as I said, cubic is the most symmetric, right? So cubic So cubic is the most symmetric. So if we look at a cubic crystal system, so let me try to draw a cube. Okay. So if this is my A side, so this is B, this is C. So A is along which axis? So this is the x-axis. So conventional axis I am choosing. B is along y-axis, and this is my z-axis. So ABC, and we have the angles, right? So how do we calculate the angle? So opposite to B, we have beta. Opposite to A, we have alpha. Opposite to C, we have gamma. So in order for it to be cubic, it's necessary that A is equal to B is equal to C, and alpha is equal to beta equal to gamma equal to 90 degree. So this is the requirement for cubic system. Now in cubic, if we look at, so cubic also we have some classifications, right? At first we have the primitive, then we have the body centered BCC. So we have the C centered. This can be A or B or C, but conventionally we call it as C centered. And then we have the FCC. So in primitive, what happens? Only the corners of the cubic unit cell, they have the atoms. BCC means in addition to the corners, at the center of the cube there is an atom. C center means any of the parallel to faces, so they have the atoms. And in FCC means all the faces in the middle there is one atom. So you can understand, among the cubic, FCC will be the densest. So this is the face centered cubic. So at first we have cube, and then inside cube we have the face centered cube. So we will learn about dislocations in the FCC. So this previous which I showed, so this simple dislocation, this is not true for FCC, because in FCC there are two missing planes instead of one. So how are these missing planes coming? So if you look at the video from the professor, so you will see that he has given the derivation and everything. So I am not repeating that. But the key points for FCC which you need to remember is that first thing, that there are two missing planes instead of one, and the second thing is that the dislocations can dissociate into partial dislocations. Okay, the Berger vectors can dissociate into partial. So Berger vector now we will understand one by one. So I am moving forward. So to understand this, at first we will what we will do is we will learn some basic crystallography, right? So some points about basic crystallography is that when we are defining an unit cell, in order to define a lattice, we need to give the origin point, right? So the origin 0, 0, 0, and then if we have a cubic system, as we saw earlier, so in cubic system, this A, B, C, they are all equal. On top of that, the alpha, beta and gamma, they are all equal and is equal to 90 degrees, means they are all orthogonal to each other, the faces. That is why when we talk about this family of planes, it includes all the 100 as well as the negatives, right? So we will learn that also, and it is very important so to understand the significance of the brackets. So in crystallography, so 1 bracket denotes one different thing, right? For example, this This is used to denote when we write like this separated by commas. So this denotes the coordinates, right? So this means, so these are the coordinates. And if these means this is also first bracket, this is also first bracket. With when there is a comma, then it is the coordinates. Without comma, this indicates the planes. What is this? This within curly brackets. If there is curly bracket, then curly bracket denotes family of planes, equivalent planes. Okay, so this is what is written here. The notation HKL denotes, within curly brackets, denotes the set of all planes that are equivalent to HKL by the symmetry of the lattice. So this is equivalent family of planes. Okay, so how to find out these planes and directions? So here you will need to denote the planes as well as the directions, because when you go further on about the Berger vectors, the Thomson's tetrahedron and all those things, you will need to understand how these directions are placed, and you shouldn't do Tamar kind of thing. You should be able to understand how these directions are coming. It's very basic things, right? So we will go through that. So Miller indices, for the notation which we use is obviously Miller indices. So we all know that. So how to denote the crystallographic directions by using Miller indices, right? So we will follow this. So at first we know we use the right-handed coordinate system and find out the coordinates of 2 points that lie on the direction. Then we subtract the coordinates of the tail point from the coordinates of the head point, right, to obtain the number of lattice parameters traveled in the direction of each axis of the coordinate system. Then we clear the fractions and everything, enclose them in square brackets, and if there is a negative sign, what we do is we do not write the negative sign. We do not write as -1, we put a bar over the number. So we write as 1 bar. So this is an example which I have already placed for you. So if these are 2 points, so this is one point which I am assuming to be the origin, so it is 0, 0, 0, right? So if it is to be exactly correct, I should put the commas, right, like this. So this is the 0, 0, 0 origin. This is the, suppose, 0, 1, 0. Okay. So if I want to know this direction, if I am interested to know this direction, then which is my head and which is my tail? So this is my tail. So this point is my tail and this is my head. Okay, so what I have to do, I have to subtract the coordinates of the tail point from the coordinates of the head point, right? So I will write the head point. So this 0, this is 1, don't confuse it. So this is 0, 1, 0, and then this is 0, 0, 0. And then I will subtract. So if I subtract, so 0 minus 0 is 0. So if I subtract 0 from 1, I will get 1. Then the 0 from 0 is again 0. So this becomes my direction, right? So this direction, so what is this direction? This is my 0, 1, 0 direction. So this you can think that this is easy. Why? Because it is origin. Origin means all the coordinates are your 0, 0, 0. So from origin, if suppose this would have been something with coordinates 1, 3, 5. So I am just giving arbitrarily. Then obviously this direction will be 1, 3, 5. Because if you subtract 0 from this, it will be the same thing. So this direction will be 1, 3, 5. Will it? So no, because we have to clear the fractions and reduce to lowest integers. However, so in this course, in this syllabus, we are restricted to cubic system, so where we will not go to this higher indices, right? Okay, so let's move on. So yeah, if this is your cube, this is your cubic system. So so this is my x axis, this is my y axis, this is my z axis. So this is the origin. So I hope I am audible, right? So this is my origin of 0 0 0. Now we have when we are drawing the directions and when we are drawing the planes, so we saw in the previous slide, so there is one particular notation for planes, Miller indices for planes, and one particular notation for the Miller indices of the directions. So at first let us look at the planes. So this is quite interesting. So if this is the x-axis, this is the y-axis, this is the z-axis. So of course along z-axis this will be my 0 0 1 plane. Along the x-axis this will be my 1 0 0 plane. Along the y-axis this is my 0 1 0. Now for cubic what will happen is these three will become equivalent. Why? Because the angles are 90 degree and the sides, the ABC, the length of the sides are equal to each other. So these three are equivalent in case of cubic systems. Yeah. So now for if we go to the other planes, so this will be my 1 0 1 plane, this will be my 1 1 0 plane, and this is my 0 0 1 plane. Now the most interesting and important part, the 1 1 1 planes or the 1 1 1 family of planes, means all the planes which are equivalent to 1 1 1, that include 1 1 1 and their negative. So in cubic, in FCC this will be very important for us. So we will learn how to denote these planes, right? So if how to denote this plane, so if this is my origin, right, I am considering it as the origin. So how to find out the Miller indices for planes? So what we have to do is we have to identify the intercepts on the x, y and z axis. We have to identify the intercepts, specify them in fractional coordinates, and take the reciprocal. And when we are taking the reciprocal, we will get the Miller indices. Now for that we have to remember one small thing. What is the reciprocal of 1? The reciprocal of 1 means 1 divided by 1, so we will get 1. However, the reciprocal of infinity will be 0. So here if this is my plane, so what is the intercept of this plane on the three coordinate axes, that is the x, y and z, right? So along my x, so this is what is this coordinate? So this is 1, right? So it is putting, this plane is putting an intercept of 1 along the x-axis, because it is crossing here, means one full unit cell length has passed, so I am taking it as 1. Along y-axis it is cutting the full length along y, so this is also 1, and then along z this is also 1. So it is touching the x, y and z coordinate axis after one full unit cell length. So we are getting as 1 1 1, and if we take the reciprocal, it is the 1 1 1. So similarly you can find out about 1 bar 1 1, 1 1 bar 1 and 1 1 1 bar, right? So what will be the 1 1 1 bar? So it will be the opposite plane. So here it is not given, it will be like this. It is going very bad. Let's wait. Discard. Let's check the recording. So this is about the crystallographic planes. Now we will talk about the directions. So if this is my origin point 0 0 0, so what is this is my coordinate. So what is this coordinate? This is 1 1 1 coordinate. So this is my 1 1 1 direction. Now this is something which is called as the body diagonals, because you can see in this cube, so this face is behind and this face is in front. So in behind from this face, this diagonal is coming to the front. So if you imagine one room, when it is crossing the entire room, suppose from one corner it is coming out into the front to the other corner. So it is cutting across the whole room. So that is through the whole body. So it is called as a body diagonal. So in contrast, if you are imagining a direction along a certain wall of the room, or in other words along a plane, so then that will become a phase diagonal. So like this diagonal, if you consider a direction from here to here, so here this is what, this is the tail point and this is the head point. So let us try to find out the Miller indices for this direction. So this is your tail, this is your head. So we have to subtract the coordinates of the tail point from the coordinates of the head point. So we will write 1, 1, 1, 0, 0, 1. We will subtract. 1 minus 1 is what? 0. 0 subtracted from 1 is 1. 0 subtracted from 1 is 1. So then my this direction is what? This 1, 1, 0 direction. So this 1, 1, 0 direction is also very important in FCC, right? So you have to remember how we got it. Okay. So a little bit more about this basic crystallography. So if we consider this face-centered cube, so we learned in the previous slide only. So this is my 1, 1, 0 direction, right? So this is my 1, 1, 0 direction. Then what will be this direction? So for this we have to subtract the coordinates of this tail point from this head point, right? So let us do it quickly over here. 1, 0, 1, 0, 1, 1. So this will become 0. So this is what? This is minus 1. You cannot write, right? So you will have to write minus. So if we are if we are subtracting 0 from 1, it will be 1. But you cannot subtract 1 from 0. No? So it will be, if you are trying to subtract 1 from 0, it will be minus 1. And then you are subtracting 0 from 1, this is 1. So this direction, so it is already given here 1. This part will become 1 bar. 1 bar 0. Okay. So like this you can find out all the directions, right? So that is why I have provided you with all the coordinates. So if this is my origin 0, 0, 0. So this is my 0, 1, 0 coordinate. This is my 1, 1, 0 coordinate. This is 1, 0, 0 coordinate. And this the coordinates. So now you can find out all the directions, right? So suppose I want to know what is this direction. So for that we have to subtract the coordinates of the tail point from this head point. So since this is 0, 0, 0, I can directly write it. What? 1, 1, 0. Now you will see one interesting thing. This 1, 1, 0 direction we got previously also. So how we got here. So this means this and this. So they are what? Parallel. So if something, so because these are vectors, it is very important to understand that if you get a direction like this, which is pointing like this, so if you go up and down also, right? This side, the direction, the sense of the direction will remain the same. The magnitude can differ, but the sense of the direction will remain the same. So this is my 110, like this was my 110. Now I want to know this direction. So what will be this direction? So will it be same as this one? Yes. So this will also be the same as this one, right? So what will be my this direction? So again this is 0, 0, 0, na? So if I draw like this, so this direction will be 0, 1. Now this, in this direction what will happen? This bar will come. But what will it be? So let us find out 0, 0, 1 and try. And can I change the color of my pen? Yeah, so it is red now. Let me use blue. This is what 1, this is -1, this is 0, this is -1. Okay, so to avoid confusion, I'm drawing with other pen. So this will be 0, 1 bar 1. Okay, interesting, right? So similarly, if you now you can see this will also be the same, right? If you are subtracting 100 from 111, then what will you get? You will get 011, this direction, and similarly this direction will be replicated here. So now let us try to know this. So this is one phase diagonal. This is one phase diagonal. These are all phase diagonals, right? What I am drawing. So if I consider this phase and I draw a diagonal like this, let me change the color. Green. So what is this direction? Okay. 1, 0, 0. We will subtract 0, 0, 1. Okay. So what will this be? 1 subtracted from 0 will be, yes, -1. This will be 0. This will be 1. So let me check it out, and this is -1. So this, okay, so this direction is 1, 0, 1 bar. So similarly, this will be directly what 101, right? Because this is the origin. So I am not I'm directly writing that. This. However, from this to here will be my 111, which was the phase diagonal I showed before, right? Okay. So now one important question is that in case of FCC, what is the closest packed direction? Okay, not the closest packed plane. The question is that what is the closest packed direction in FCC? So how to know that? So if we draw FCC, okay, so this means that there is atoms here, here, here. Let me first draw the primitive one, then I will put the center atoms. Okay. So if you see there is one atom here. Similarly, it will be on all the faces, but I am drawing only for this face. So don't think it is wrong or something. I am drawing only for this face. Why? Because all the faces are equivalent. Because why? Because this is an FCC. So you have to remember that. So here, this is what? This is a this here looks, it looks like this is a very there is a lot of open spaces, right? Why? Because this is ball and stick model. Okay, so just forget this. We will come back sometime later. So just let me delete. Why? Because it's not needed here. Huh? The recording. So we are going to leave this ball and stick model, although it is very useful, but to understand what is the closed packed direction, we need to view the closed packed model, so which is the hard sphere model. So if hard sphere model means it will fill up the entire space. So you can imagine that if we look at this direction, or this direction, then along that direction, the vector, okay, if we think of a vector like going from here to here, it is touching atom in some atom at some point or the other. Okay, so let's try to understand that. So now I will draw this as hard sphere model. Let me change. Yeah, it is fine. Okay, so hard sphere model means, so I suppose I want to go along this direction. Okay, so in the center there is one atom like this, at the end there is one atom like this, at this end there is an atom like this. So I am drawn very badly, so just excuse me. Okay, so what I am trying to say is you have to take all these atoms as same size, right? Because the lattice will consist of the same material, means all the molecules or all the atoms will be same. So their sizes will also be same, but while I'm drawing by hand it's becoming a little difficult. So let me just try it like something like this and this, like this. Okay. So in this direction, if I think of now, so it is touching all the atoms at some point. There is no blank space. So the closest packed direction in FCC. So what is the answer then? One second. Yeah. So the answer is that this 110. Pen. 0 is my closest packed direction. Then does this mean that this direction is not your closest packed direction, or this direction is not your closest packed direction? No. Why? Because all these directions are equivalent to 110, right? So we have seen here, right? So this is 110. This is 110. Now this is what? This is 011, which is equivalent to 110. Then this is 011 ones. So equivalency of planes are written in curly brackets. In directions, how to write that? We write using these brackets. So these notations are very important in crystallography. So this means all the equivalent directions. So this means equivalent directions. Okay, so let's move on. Now we are learning about the FCC, which is the French centered Q. So we also have the HCV, the hexagonal close pack. So this is a very age-old question, right? That which one is thermodynamically more preferred? So the ABC stacking versus the ABAB stacking. So let us learn. Like we will do a quick recap of that. So let us assume this is a set of, this is my first layer. So let me name this. So suppose this is my A layer. Now on top of that I am putting another layer. So then that is my B layer. So now when only my A layer was there, and then if I consider my only the B layer, then only B layer in itself is not anything different from the A layer. But when I am trying to place the B layer right on top of the A layer, so there is only one way I can put it, right? So even if I move a little bit this side or this side, the whole structure will remain as it is. It will remain the same. Now when I am going to place a third layer, then what will happen? Sorry, I can place it, the third layer means another spherical atom. So let us assume, let us for simplicity, let us first talk about only one atom from the third layer. Okay, so the third layer, it will be like this. So if I take one atom like this, so that atom if I can place here, so you see this white portion means what? Nothing has fallen on it till now. So that is my position 1. Now there is a second position. If I place the atom here, which means that this atom, the third layer atom, will coincide with the first layer, this atom. It will be directly on top of the A layer. So that is my position 2. So there are two ways to place the third layer. Okay. So if this is the third layer, then I can place it in two positions, right? So at first we will place it on this open position, the position 1. So then this will become my FCC, or the face centered cube. So along this FCC, so how are we going here? So we have to remember that we have gone from the ball and stick model to this hard sphere model, right? So here you see this was our hard sphere model. So here if I take my 111 plane, okay, if I take another color for the plane, because for directions I am using the blue color, so for the planes let me use the green color. Okay, plane here to avoid any confusion. The 111 plane will be like this. If I draw the atoms, okay, so there is one atom here, right? So this is for the top face. For this face there is one atom here, this one atom here, an atom here. For this front face, so there will be one atom like this. So if I am looking from the top of the 111 plane, then it will appear to me something like this, right? So where I was, yeah. So this is the 111 plane. Now where is the 111 direction? So these are the 111 directions. Okay, sorry. So these are our 110 directions. So the next question is that where is the Berger vector? So this is where is the Berger vector? So we will learn about the Berger vectors in FCC, but before learning about Berger vectors in FCC, so we will learn about that what is a Berger vector, right? So we will learn some basic understanding about this Berger vector. Okay. So these we are learning about dislocations, right? So there are two primary types of dislocations. So one are which can move and one which cannot move or glide. So the ones which cannot move or glide are immobile and which can move or decide. So we will come back to this later. But in Berger vector, so a dislocation can be characterized by the distance and direction of movement it causes to atoms, which is defined by the Berger vector. So what is Berger vector? It is a very useful concept using which we can quantify the distance and direction of movement of atoms in and around a dislocation. Okay. So we will take a short break. So it's a very long 2-hour class. So I will just some water. So please excuse me for 2 minutes. Okay. So we were at the Berger vectors, right? So what is a Berger vector? Okay, sorry. Please excuse me. So Berger vector of a dislocation. So it is basically a crystal vector, which is again specified by Miller indices, which quantifies the difference between the distorted lattice around the dislocation and the perfect lattice. So what is it basically? So if we have a dislocation, so if there would have been no dislocation, then the lattice would have been perfect. Now some dislocation has happened, so there is some distortion in the lattice. So the quantification of the difference between the perfect lattice and the distorted lattice is called as the Berger vector. So Berger vectors, it denotes the direction. So hope you are following. So Berger vector denotes the direction and the magnitude of the atomic displacement that occurs when a dislocation moves. So this is an alternate explanation. Magnitude. So this is a vector, so it will have both magnitude and direction. Okay. So let us understand the preliminary concept of a Berger vector of a dislocation in a two-dimensional primitive square lattice. So for that purpose, we will use a illustration. Okay. So this is what? This is a two-dimensional primitive square lattice. Okay. Now here is what has happened, a dislocation has happened. So you see, so the word, where is the extra half plane? So you remember, so this is the extra half plane, so this is the dislocation, right? So now we will trace around the end of the dislocation loop, okay, like this. So what to do, let us start from here. So this is one unit cell, so one unit cell let us assume to be 1. Okay, so we will record the numbers, the lattice vectors. Okay, so we will record the lattice vectors. So from here to here is 1, here is 1, here to here is 1. So 1 1 1, which adds up to be what, 3. So I have written here 3. Now along this direction again 1 2 3, so I have written 3. Now moving along here, so here 1 2 3, so the dislocation is here. We have to go up to here, we cannot come here, no, because we have to trace around the end of the dislocation. If we would have gone up to here, the dislocation is not complete, right, because these atoms are also dislocated, so we have to go up to here. So there is 1 2 3 4, so it's 4. Now I will come back here, this is again 1 2 3. So we recorded the number of lattice vectors, right? So we can count also. So 4, so this was what we started from here, 3 plus 3 is 6, 10, 13, right? So here is 13. Now we have to draw out the perfect lattice, which means that if the dislocation was not there, then what amount or length of the path I would need to traverse. So what I have to do, in the perfect lattice I have to trace the same path and move the same number of lattice vectors along the same direction as before, right? So I started with this point, right? This was the point where I started. So here also I will start with this point. So I will go 1 2 3. So this is 3, this is 1 2 3, here it is 1 2 3 4. So let me not hurry, I will show you. 1 2 3, 1 2 3, this is 3, this is 1, this is 2, this is 3, 1 2 3, 1 2 3 4. Come back here, 1 2 3. Now what I am seeing is that here, here I after coming back 13, I could rejoin, right? But here I am not able to join. Why? Because this is not the deformed lattice, right? One second, there is some noise. Okay. So so in my perfect lattice, when I came back up to here, so 3 plus 3 6 10 13, so you can see this much is the difference, right? So this is nothing but my Berger vector. So Berger vector is normally denoted as what? It is denoted as V. So it is how much is the Berger vector here? The magnitude, it is one lattice vector, right? From here to here. So this is a simple schematic illustration to understand the Berger vectors before we move into Berger vectors of FCC. Okay. So then we understood what is it. So Berger vector of a dislocation is a crystal vector. Specified by Berger vector of a dislocation is a crystal vector specified by Miller indices, which quantifies the difference between the perfect lattice and the distorted lattice. Okay. So now in FCC we learned that this was our what? This was our 110 direction. So then what is the Berger vector? So you should be able to answer this to me, right? So what is the Berger vector in case of FCC? So it is along that direction, and what is the magnitude? It is half of it. Sorry, it is half of it, right? So it is, how is it written? It is written as A by 2 1 1 0. This is the Berger vector in case of FCC. Okay, so now we will go into dislocation locks. Oh, no, sorry. So before that we have the Thomson's tetrahedra. Okay. So this one plane we learned, right? So we are skipping that now because this detailed learning about how to find out the directions and also already I have shown it before. You remember, right? So here we saw, yeah. So here in details we have seen. So I am not repeating that again. So I am going forward. Okay, 111 plane. So this is the 111 plane. Then this is the 111 bar plane. So if we take out, so this is my 111 plane, right? So if I take out this plane, okay, this 111 plane. So this coordinate is what? This is my 001, this is my 010, and this is my 100, right? So these directions and all we have found out. So from these planes and its directions, we come to what is known as the Thomson's tetrahedra. So what is Thomson's tetrahedra? We will learn. So at first, what we are focusing on? We are focusing on the three-dimensional face-centered cubic systems, right? So we have, these are the lattice points. So this is what? This is primitive, this is body-centered, this is face-centered, right? So the cubic unit cells. So this is what I was talking about. So this is the hard sphere, and this is the close packing. Okay, so actually for simple understanding we draw the cubic unit cells like this, but in reality the face-centered cubic systems, which are primarily composed of metals and alloys, so they are close packed. Okay, so sphere, this is also called as a sphere filling model. So in reality this primitive unit cell, this primitive cubic unit cell looks something like this. You see the edges is occupied by the atoms like this. Now this is body centered, so this looks like this. So what happens, there is one atom in the center. So, and also you have to remember that these all the atoms, here it is shown by another color just to differentiate it, that this orange atom is at the center, but it is not a different atom compared to what atom is placed on the edges. It is the same atom. Why? Because when we are talking about the crystal structure, the crystal lattice is composed of the same atoms of the same material. If it is an aluminum system, all the atoms will be of aluminum, right? So they are same, they are exactly equal. So just the difference in color is for better visualization. So when this is at the center, since this is the similar atom as the edge atom, means it is not something smaller. So it is not cation anion packing, right? Like NaCl structure we know, we will see also in the later classes. So here, since this is of the same size as the edge atom, so if this is sitting in the middle, then the edge atoms cannot come close together and close pack. Means it cannot be in touch with each other. Like here, it was in touch with each other. It is these two atoms, this atom and this atom is in touch with you, but here it cannot be because in the center there is one atom. So this is the body centered cubic. Now when we go to FCC, so this is the face centered cubic. So here you can understand that when we are talking about FCC, we learned that what is the close pack direction. We saw that this is the close pack direction, right? However, this direction is not the close pack direction. Okay, so we will learn about Thomson's tetrahedra. So yeah, this still now we know this, that the closest packed planes in FCC, So this is in FCC, right? Sorry. Yeah, in face-centered cubic system. So the closest packed planes are the 1, 1, 1, and the shortest distance between the atoms is half of 1, 1, 0, which is the Bircher vector actually. So what is Thomson's tetrahedron? So we will look at this slide and then we will come back to this slide. Okay, then it will be easier to understand. So how to get a Thomson's tetrahedra is basically, so this is the face centered cubic cell. So this is my 1, 1, 1 plane, right? So how many 1, 1, 1 planes are there? There are 4 1, 1, 1 planes, right? So inside this cube, so we have outlined all the 4 possible 1, 1, 1 planes and we see that it forms like a tetrahedron. So what does that mean? So this was one plane. Okay, now this is another plane. So this is what, this is 1, 1, what you should be able to say. So this is 1, 1, 1 bar. So this is another 1, 1, 1 plane and this is another 1, 1, 1 plane. So like this, if we take it out, so at the back there is one plane, this is the second plane, this is the third plane, this is the fourth plane. In the back there is one plane. Okay, so I hope you are able to understand. Otherwise I can like draw it. Okay, one second. So at first let me start with red. This is one plane. Green. This is another plane. Blue. Third plane, and then where is the fourth plane, which is any color left? Okay, red, blue, okay, yellow I can use, yeah. This is the fourth plane. So inside this cube, so we have outlined all the 4 possible 1, 1, 1 planes and we see that it forms like a tetrahedron. So in this 1, 1, 1 plane, so the edges are what? So you remember, right? So what is this? This is 1, 1, 0, right? So this direction, this is a 1, 1, 0 direction, right? Similarly, all these directions are 1, 1, 0 directions. Hence, we have these 1, 1, 1 planes, right? We have these 1, 1 planes and the edges are giving us the 1, 1, 0 direction. So, what are the edges? The edges are nothing but the corners of this triangle, right? So, in simple words, we will say the corners of triangle are actually the edges. So, the edges are giving us the 1, 1, giving us the 1, 1, 0 directions. Okay. So what are the unique features of this tetrahedron? Okay, firstly the tetrahedron is equilateral. Secondly, all the edges are actually along the 110 direction. So this tetrahedron is something special, right? So this is nothing but the Thomson tetrahedron. So in Thomson's tetrahedron, what happens is, so all the possible 111 planes, all the possible 110 directions in that particular plane can be identified using this tetrahedron. So this is the Thomson's tetrahedron, but this is what? So this is a 3D, three-dimensional structure, right? So this is a three-dimensional structure which is projected into 2D, into the plane of a paper, or in this case the screen of my computer. So it is projected onto a flat 2D screen. However, this is actually a three-dimensional structure, so we can open it out, right? then we will get something like this. So this is the Thomson's tetra. It is a theoretical concept which is very useful to understand the the dislocation in case of this FCC. So in for Thomson's tetrahedron, so what are the two points? First point is that it is equilateral, and secondly the edges represent all the possible equivalent 110 directions. Okay, so the flat projection, sorry, so the flat projection of this tetrahedron is very useful. There are 4 slip planes with 3 slip directions for each. Only 2 of them are linearly independent. So please you don't need to worry. So what do you mean by there are 4 slip planes? So what are the slip planes? So the 111 you see, these are the 4 slip planes, okay, with 3 slip directions each. So what are the slip directions? So these 3, nothing but these 3 are the slip directions, okay. So we learnt about this Thomson's tetrahedron. So the edges, one second. So the edges of the Thomson tetrahedra are given by connection of the 4 nearest neighbors. What is the important thing to note about Thomson's tetrahedra is, the first thing is that the Thomson's tetrahedra is not an unit cell. It is just a concept. Okay, it is not possible to obtain a perfect crystal by translation, symmetry, or application of other symmetry operations on it. So what is that? That is the definition of a unit cell. So what is the definition of a unit cell? That if we apply translation, symmetry, and other symmetry operations on the unit cell, we will get the whole lattice. We will get the whole crystal. However, the Thomson's tetrahedra is not a unit cell. It is not possible to obtain the entire lattice by repetition of this Thomson's tetrahedra. And another thing is that the Thomson tetrahedra connects the nearest neighbors and not the corners of the conventional unit cell. Okay, so that is about this Thomson's tetrahedra. So if we take this 3-dimensional thing, so if I rename this, so if I take the edges, so what are the edges? So can you find one point where all these 3 are connected? So if you see here, so this was my, where is my pen? So you see, this is A, this is B, this is C, and this whole, there are 3 D's. What does this mean? This means these D's are like, if this is the flattened projection, right? So if you imagine this as a 3-dimensional, so what will happen is, so this will kind of go down, this will go back, this will go back, and it is basically the same point. Okay, so it is like, this is my A, this is my B, this is my C, then this point below, this is my D. Okay, so I have just flattened it out. So this is very useful to understand what, sorry, okay. So here using Thomson's tetrahedra, why this is useful? Because directly it is possible to visualize all the 111 planes and the 1110 directions in that particular plane. Okay, so I have many slides left. So now we will move on to dislocation locks. So lock means what? So something is locked, it is not moving, right? Something like this. So here we will talk about the locking of dislocation. So what type of dislocations would form a lock? Okay. So in case of face-centered cubic systems in FCC, all the 111 planes are the glide planes and form the part of the slip system. We saw that previously. So from the Thomson's tetrahedra, and if we take two planes, suppose 111 and 111 part, then on which plane will the dislocation, log lie? So let us see. So here if we take this FCC unit cell, so we have the x, y and z coordinates and the directions for reference I have given. Now if we have this 111 plane and then this is my 111 bar plane, then you can at like up front you can see that it is sharing one common edge, right? So this edge, so let me go to pointer. Yeah, so it is sharing this common edge, right? So this is my 111 plane, this is my 111 bar plane. So and as we know in case of FCC, so the for this 111 family of planes, the edges represent the Berger vectors. So if I take out these two planes like this, so this is my 111 and this is my 111 bar plane, then if I consider these two Berger vectors, okay, so for this 111, so this is my Berger vector which will be half of this, so I have drawn the magnitude as half. And for this 111 bar plane, if I take, so if I take these two sets of Berger vectors, then what will be my net result? And it will be something like this, right? So what is this direction actually? So if we place the cube, so this is nothing but this 110 direction which is lying on this face. So what is this face? Is 001 face, right? So the Berger vector, so if there is a dislocation lock, the Berger vector of the resultant dislocation will lie on the 001 plane. Okay, so this is the conclusion, that the Berger vector of the resultant dislocation will lie along the 001 plane. Okay, so now we will come to something which is known as the partial dislocation. So when there are partial dislocations, then what happens is the partial dislocations, they leave behind a stacking fault. So there are two types of partial dislocations. So one is the Frank partial dislocation and another is the Shockley partials. So we have seen before that partial dislocations can be of two types. So one is mobile and another is immobile. So glissile means it can glide, means it is mobile. So the Shockley dislocations are glissile type, whereas the Frank partial dislocations are of sessile type. So we will look into that in more details. Okay. So this is the Frank partial dislocation. So what is this? So the Frank partial dislocation is formed as the boundary line of a fall formed by inserting or removing one close packed layer of atoms in the 111 plane. Okay. So how to see? So this is suppose we are seeing this. So we are looking say on from this 111 plane. So from that if this is the 111 plane, then from that direction we are seeing. So Frank, so let us try to understand this. So formed by inserting or removing one close packed 111 layer of atoms. Okay, so this is what? This is the 111 direction. Okay, so you know that for any plane, so if this is a plane, then what is the direction is always normal to it, right? So I hope you know this. Just let me show you. So if I take a cube, yeah. So this cube only I can take, right? And let me take the coordinate axis also, it will be easy. So if this is my so this point, so what is this point? This is my 1 0 0, right? Similarly this is my 0 0 1. This is my 0 1 0. So this plane, what is this plane? This is coordinate. So this point is the 0 0 1 coordinate, but this plane is the 0 0 1 plane, right? This plane. So this is my 0 0 1 plane. And this is my 0 0 1 direction. So direction is always perpendicular to the plane. Direction is always perpendicular. So the direction is always perpendicular to the plane. Okay, so similar, it is a similar for the other planes also, right? So for example, for this plane, so what is this plane? So for example, what is this plane? So this is the x-axis. This is the 1 0 0 plane, and this is the 1 0 0 direction. Similarly for this, right? So you have to remember this. Direction is always perpendicular to the plane. So here we are looking at these planes of atoms. So one rows of atoms. So this is the 1 1 1 1 1 1 1 1 1 1 direction like this. Okay. So now what has happened here? This was the A layer. Okay, this is the A layer, this is the B layer, this is the C layer. Now here what has happened is, this is a dislocation has been formed. This is the extra half plane, and then there is this missing plane. So there is one dislocation here. Now how this is formed? This is formation of formation of 1 by 3 1 1 1 frank partial dislocation. Means along the 1 1 1 plane, 1/3 of the atoms have moved. Okay, by removal of a part of a closed packed layer of atoms. So this frank partial is an edge dislocation here, and here the Berger vector is not contained in one of the 1 1 1 planes. It cannot glide and move conservatively under the action of an applied stress. Such a dislocation is said to be sessile and can only move, however it is to be remembered that it can only move through climb. Okay, however it is sessile. Now, apart from frank partial dislocation, so what is another type of dislocation which is known as the Shockley? So there is a Shockley partial dislocation, right? So the Shockley partial dislocation has its Berger vectors lying in the plane of the fault, and hence it can glide, means it is glissine. So how is it in case of FCC? So this is for FCC. For this it is represented as 1/6 of the 111 of 112 direction. Okay, however, in case of frank partial dislocation, the Berger vector is normal to the 111 glide plane, and so the dislocation cannot glide. It is represented 1/3 of 111. So you have to remember these two differences. Okay, so if it is asked, so what are the two, what are the basic differences? List out the basic differences between the frank and the Shockley partial dislocation. So we have to remember, one is about its mobility. So the frank partial dislocation cannot glide. The Shockley partial dislocation can glide. So what is the reason? The reason is that the one which can glide, because there the Berger vector lies in the plane. And here in case of frank partial dislocation, the Berger vector is normal to the plane. So the dislocation cannot glide. And also the representation. So the magnitude. So this is 1/6 of 112 and the frank is 1/3 of 111. So these are the two basic differences. Okay. Now we come to the last part of this topic, so which is another type of deformation which is known as the twin boundaries. Okay, so now we will learn the what is this twin boundaries. So if we take this cube, this FCC, and we take this 111 plane and we list out the direction. So we have done this many times, right? So what am I trying to do now is I am trying to show you how I can go from here to here. Okay, so here, see, if this is my 111 plane. Draw. Okay. So if I am looking from the top, so from top of the 111 plane, then one after the other I will see, see these are the planes like this, and on top of that it will sit like this, something like this. So I'm not going to that, but now what I'm doing is I'm looking from the side. So if this 111 plane I have put here. So this is my 001, this is my 010, and this is my 100. Okay, and these are the directions, the Berger vectors. Now I am looking from this side. Okay, so here there will be the atoms, right? So here the atoms are here, means there is one atom here, there is one atom here, there is one atom here. So when I am looking from this side, it will look to me something like this, right? So this is how it is. So this is my first layer. So this is actually my A layer. So this is also a plane. I am looking just from the side. So my plane is coming to me like a row. So this is my A layer. This is my B layer. This is my C layer. Okay. So on top, this is FCC. So you have to remember this notation is exactly the same as this notation. I'm just looking from the side now. Okay, from one side like this. Okay, so my first layer of atoms is my A layer, then my second layer of atoms is my B layer, and my third layer of atoms is a C layer. Then after this, again this A layer is repeated here. So again this is my A, this is C. So this and this is exactly same. is exactly the same. Similarly, this and this is same and this is same. So this is what? This is A, B, C, A, B, C type of packing, which is FCC. Now, this plane was there. Okay. Now, in case of FCC, what happens? There is a possible layer stacking, what we call as the ABC type of stacking. So that is exactly what we saw, right? Sorry. Okay. Okay. So this is the ABC type of stacking. Now, what are the twin boundaries? So twin boundary is a kind of grain boundary. Sorry, twin boundary is a kind of grain boundary whose lattice structures are mirror images of each other in the plane of the boundary. So means mirror images of each other. So how mirror image means what? Means mirror image basically means a reflection plane. So how are we getting to that reflection plane? So we will see that. So another type of the twin boundaries. So to understand the twin boundaries, so first we will look at the stacking fault. Okay, previously we saw this. So if there is a partial dislocation, which gives rise to a stacking fault, we have this ABC. Now if this partial dislocation is applied, so this is the Berger vector, such that this row of atoms, this layer is moved by 1/6 in this 111 in this 112 direction. This is the 112 direction. So it is moved by this much. Then what will happen? This will shift kind of here. So this will shift here in such a way. So this is so here I am not able to show the the video or the animation. So if you go back to the class of the professor, so in the last part, in the last lecture, when in the last part of the lecture 5, where he talks about the twin boundary, so you can see it very nicely. So what happens is, so I'm telling you the conclusion, that this was the previously A layer, right? So the previously, which was the A layer, it becomes the B layer, means this superimposes on top of this. Okay, like from here it was starting. So just one second. So what I'm trying to say is, suppose this atom is starting from here. So if I draw a line here, so this atom will also start from here. Okay. So let me show that to you. Yeah, so this becomes, this is the new one, so I am changing the color, yeah, so this is the, so this was what, this was A, this has now become the new B. So the previously A layer will become the B layer. So it is something like this. So for easy understanding, so if you see, so this is A, B, so initially it was what? This is FCC, right? This is ABC, then ABC. Now after this dislocation it has become ABC, then it has become B. Similarly this will become C. Then after that again this same thing will continue. So here this is the final lattice, right? So this stacking fault is stable. So this is the partial dislocation. Now what happens in case of twin boundaries? Here what happens is each layer is displaced by the same amount. So previously only one layer was displaced. Here these three layers, each of them is displaced by the same amount. Okay, then what happens is it comes down to something like this. So then what here what happens is that this comes directly under this is exactly becomes like this, and this becomes exactly like this. So if I draw, if I give the old notation, so this was ABC, so this was supposed to be A, this was supposed to be B, this was supposed to be C. So my previous A has become my new B and my B has become my A. So so this is called as the twin boundary, and this looks like there is a reflection plane here. So this is called as the, this is an additional mode of deformation in case of metals and in case of metals and alloys, which is called as the twin boundaries. Okay, so the stacking, in case of stacking fault, there is the movement of only one layer, but here there is the movement of all the layers, which is displaced by the same amount. So this is the twin boundary, because it looks like as if there is a reflection plane here. Okay, this is an additional mode of deformation for metals and alloys, is twin boundary. So we learned, and in this last part, so we have learned about two modes of deformation, right? One is the stacking fault and another is the twin boundaries. Now we will compare the energetics of the two deformations, and we will compare. Okay, so previously what have we compared? Previously we compared the stackings of two different things, right? We compared the FCC and the HCP, the face centered cube versus the hexagonal flow specs. So the face centered cube adopts the ABC type of packing, whereas the hexagonal packing adopts AB type of packing. So AB, after that A is there, so A is directly over, like this A. So thermodynamically this HCP is less stable, and the FCC, where there is ABC, that is more stable, right? So FCC is more stable than HCP. So there we compare the energetics of the stacking. Now we will compare the energetics of the stacking faults. Okay, so it's very interesting. Let's do that. So energies associated with the stacking faults and grain boundaries. Okay, so if we, so here we will this is the energy of the twins. This is the, so I'm giving E for energy, ESF, and this is E twin. Okay. Let me check everything is fine. So in case of the stacking falls, what we saw that only one layer is moving. So the ABC type of packing was there, and then this layer moved by 1/6 along this direction, which gave was by which this A layer became the B layer, and this B layer will become the C layer. Like this it will go on. So here what originates is called as the stacking fault. So this SF. So here this is the stacking fault, and what originates here is the stacking fault. Okay, this is after one layer movement. Now when we come to twin boundary deformation, what happens is this same dislocation is applied for all the layers. One second, it is and so I'm sorry, just I need to rearrange my slide. Okay. So now let us start from the beginning. So we will understand the energies associated with the stacking faults and the twin boundary. So at first we will look at the stacking fault. So here only this layer has moved, giving rise to a stacking fault here. But here what has happened, here all the three layers have moved such that this yeah. So here this is initial, okay, this is initial and this is final. Why? Because this, in case of the stacking fault is stable. Okay, this one layer stacking fault, when it has moved, so this is stable, so this is the final. Now in case of here, this is the initial, this is the final. So here what has happened is this A has remained as A, but this C here, this twin boundaries or this reflection plane is generated in such a way that this A layer has now become the B layer. Okay, and this B layer has now become the A layer. So these are the two main differences, right? So you can see that in the final stacking, so what is the stacking sequence in case of SF? So there is ABC, then BCA type of packing, whereas here there is ABC, AB type of packing. Now we have to compare the energetics. Okay, so which in initially both are same, right? So in the final, which one is more energetically stable and which one is more energetically unstable, we will look at. So how to see? So we will look at this here. So here this A layer was there, then this B layer, then C. Now this B layer is there, which is directly on top of this B layer, right? So there will be a repulsion between similar atoms. So let us call this repulsion as delta. Okay. Now similarly there will be a repulsion for these two as well, because this C and this C is directly on top of each other. So this delta not. Now what I keep saying, you have to remember is that since this is the same crystal lattice, so B and C atoms are same, right? Therefore so since these atoms are same, hence the repulsion terms will be the same for these two, right? So delta prime is equal to delta, and what is the repulsion term? So that is delta plus delta prime, which is equal to 2 delta, because because all the atoms are similar, so it will be the same. So it will be 2 delta. Now let us come here. So here in the middle of the plane, this reflection plane has run, right? And on top there is this layer. So as usual, like this, there will be a repulsion. Which is delta. But here previously what happened is that this C and this C layer had some repulsion, but here there will be no repulsion, because you see this is B here, so this B will repel this. However, this C will not repel this A layer here, because this is not the similar layer, it is not sitting on top, exactly vertically on top, hence it will not repel. So here if we look at the repulsion term, so it is only delta. So if you compare, these two, in case of twin boundary there is delta, whereas in case of stacking faults you have 2 delta. Hence what conclusion can you draw? So the conclusion you can draw is that in twin boundary deformations are energetically more, they have less energy, right? They have less energy than this stacking fault dislocations. So this is, I think, all. Yeah. So what have we learned today? So what is the summary? So we have learned about the partial dislocations. We have learned that partial dislocations are of two types. One is the glacial, one is the sessile. Then we learned about the Thomson's tetrahedra, which is the flat projection of the tetrahedra combining the 111 planes and their edges, which are the 110 directions. Then we learned about the dislocation logs. If we have two equivalent 111 planes like 111 and 111 bar, then they will form a dislocation log. And then we learned about the stacking faults and twin boundaries. Okay, so thank you, that's all. So we will meet in the next class, which is next week, next Saturday from 4 p.m. Okay, thank you.